Turing on computability, right? Now, in the last class, as you know, we looked at universal Turing machines, and the key thing that you should remember about universal Turing machine is the following. Universal Turing machine is a Turing machine which takes the code of another Turing machine M and an input X to for that Turing machine M in form of coded word M X pair, right? This is given as on the input tape to the universal Turing machine. And what this universal Turing machine does is it mimics the behavior of M on X. As a result, UTM accepts the code MX if and only if M accepts X. UTM rejects the code MX if and only if M rejects X. And UTM loops on code input MX if and only if M loops on X. That is because UTM basically simulates each step of working of M on X by one phase of its working, right? And additionally, if UTM is given an input which is syntactically incorrect, it halts and rejects. We saw these properties. We also defined two languages, one called MP and one called HP. MP consists of all codes MX pair such that M accepts X. On words which are not accepted by M, the Turing machine, words which are not in MP, the Turing machine may loop or it may reject. There is another language called HP. It accepts all MX pairs such that M halts on X. That is, on all words which are not in HP, M loops. Okay, so these two languages are there, and we saw that these two languages are actually recursively enumerable languages, right? That is, you can define a partial Turing machine which will accept exactly these two languages. And the key question which was there was, are these languages HP and MP recursive? In other words, the big question is whether membership in HP is decidable and membership in MP is decidable. What do we mean by HP is recursive? Whether Turing machine halts on a given input X can be analyzed by another Turing machine which can give an answer to this question within finite time, and it will definitely give a yes/no answer. That is the question. And similarly, the question is whether MP is recursive. We had raised this question last time, and the answer to these questions is no, that neither of these two languages are recursive. However, they are both recursively enumerable languages. So now we know that there are languages which are RE but not recursive, and there is a gap between them. However, establishing this is requires certain amount of work, and that is what we will be doing today. Now, the technique which is used to establish this is called diagonalization, and diagonalization has been used for showing impossibility of several things in mathematics. We are trying to show that there is no total Turing machine which accepts the language HP, and for that we will use this technique of diagonalization. So by an example which has nothing to do with Turing machines or automata, I want to explain the technique of diagonalization to them. One of the earliest diagonalization technique was to show that square root of 2 is not a rational number. And you might recall a proof of this. That proof uses diagonalization. It assumes to contrary that it's a rational number given by some ratio P by Q which is in irreducible form, and then you show that there is a contradiction. But let's look at slightly another question. So here we are saying that suppose you are given some set A. What is power? 2 to the A represents power set of A, set of all subsets of A, including the empty set, including the full set A, but only including some of the. So collection of all the subsets of A is called the power set of A, which is denoted by this. Okay, and what this theorem says is there cannot be a bijection from A to the power set of A. What is a bijection? Bijection is a one-to-one and onto mapping. So to give you an example, what a bijection, let me write it here. bijection is 1 to 1 and onto mapping. That is, the elements of A and elements of power set of A can be paired, in 1 to 1 fashion, right? And you cover everything, right? This is bijection. So let me give you an example. Suppose you have got the set of natural numbers and the set of even natural numbers. So even will contain what? 0, 2, 4, etc. Right? And natural numbers contains, of course, 0, 1, 2, etc. Right? Now we say that there exists a bijection between nat and even. To go from nat to even, right? We can define a function called twice. So twice of x will be equal to 2 times x, and so it will map 0 to 0. So twice will do the following mapping. Twice will map 0 to 0, 1 to 2, 2 to 4, and so on. Now you can see that every natural number is mapped to a unique number in even, and every number in even comes from some number in natural number. So it's a 1 to 1 and onto mapping, and it kind of pairs elements of even with elements of nat, right? And so this is a bijection. Now, those sets which have a bijection with natural number are said to be countably infinite. Okay? And the theorem here says that there is no bijection between any set A and its power set, including, you can take A to be natural number, the theorem will hold. That means between natural numbers and power sets of natural numbers, okay, set of all subsets of natural, there is no 1 to 1 onto mapping. This also says that the set of subsets of natural numbers is uncountable. In a very similar way, you can show that the set of real numbers is uncountable, right? Okay, so this kind of results are there, but we are going to see the proof of this theorem. So let me go further. How do we prove that there is no bijection from between A and power set of A? We assume to the contrary that such a bijection exists. Let F be such a bijection, and then we'll show that by assuming this we will land up in a contradiction, and the only way to get out of that contradiction is to say that the assumption was wrong and no such F exists. So that is what we are going to say. Assume there is a bijection F like this, right? Now what do? Using this F, which we have assumed to exist, we define a set B. Okay, so let me explain this set B. B is going to be some subset of A. Okay, we are going to collect some of the elements of A in it. Which elements? Take an arbitrary element x belonging to A and make this check. We have this bijection F from A to power set of A. That means F of x will be some subset of A. So F of x is some subset of A, right? Because F of x belongs to the power set of A. We look at this set F of x and check whether x itself is in F of x or not. If it is in F of x, we do not include it in set B. If it is not there, then we include it in B. So we look at each element of A and make this test, that does x belong to F of x. If it does not belong to F of x, we include it in B. This not is what is called diagonalization. We have this self-reference, and then we are diagonalizing using this does not belong. Okay, doesn't matter. The definition of B should be clear. So B is some subset of A consisting of elements which have this property. Those elements, so they don't belong to F of the element, right? This is, we have constructed B. Now remember, one property of bijective functions is that they are invertible. That you can give apply it to any element in power set of A and it will give you back an element. That is, you can now consider the inverse of this function A and let y be the element which is F inverse of this set B that we constructed. Remember, since there is a bijection 1 to 1 and onto mapping from A to power set of A, every element in power set of A will be related to some element in A. by F inverse. So we take F inverse of B and we get. In other words, we choose Y such that F of Y gives B, and there will be a unique Y which will give this B, right? So we have identified an element Y of A which has this property, that this B we constructed is given as F of Y. Okay, this is clear. So I hope this construction of B and then construction of Y is clear to you, because if you understand these definitions, then the result is going to be very clear. Now we ask this question: does Y belong to F of Y is a set? It is same set as B, and we ask whether Y belongs to this set F of Y, that is whether Y belongs to B or not. This is the question we ask. And if we try to analyze this question, we will find that whether the answer is yes or no, we will wind up in a contradiction, and that contradiction is very easy to see. The yes answer to this will lead to contradiction. No answer to this question will also lead to contradiction. So it is just not possible to answer this question. And because we cannot have any answer for this question, our assumption that F was a bijection is false. So what is the contradiction? We want to ask whether Y belongs to F of Y. So if Y belongs to F of Y is same as B, right? That is what we had defined, which is same as saying Y belongs to B. But what is the definition of B? B is the set of all elements such that X does not belong to F of X. So in particular, if Y belongs to B, F of Y does not belong to F of Y. So we get this equivalence which says Y belongs to F of Y if and only if Y does not belong to F of Y. So I can say this is equivalent to, because B is same as F of Y, Y does not belong to F of Y. So, and this proof works in both directions. So we have a contradiction: Y belongs to F of Y if and only if Y does not belong to F of Y. This is absurd. And this absurd result we got because we assumed that there exists a bijection. So this proves that there is no bijection between a set and its power set. In some sense, the power set will always have more elements than the set, right? And this is true also of natural numbers. The cardinality of natural numbers is smaller than the cardinality of power set of natural numbers. This is how Cantor defined the sizes of infinite sets, and he said there are infinite sets of different sizes, and in fact this is his proof. Okay, so this is an example of diagonalization. Now what we will do is we will use this notion of diagonalization to show that our halting problem is undecidable. What do we mean by halting problem is undecidable? Equivalently, we can state the same property as the language HP is not recursive. And what was language HP? If I may write it here, HP was the set of all MX pairs, code of MX, such that M halts on X. That is, it running M on X, the machine will either reject an accepting state or a rejecting state. Those pairs will belong to HP, halts on X, right? This is my halting problem. And we already showed that this set was recursively enumerable. Now we will show that it is not recursive. Okay, saying that HP is not recursive, in order to show that it is not recursive, we will assume to the contrary, that in fact, if it is recursive, there must be a total Turing machine which will recognize this set. So we will assume to the contrary that it is recursive, and hence there exists a total Turing machine K such that the language of the Turing machine is same as HP, right? This is the definition of a set being recursive, right? To elaborate on this, that there is a total Turing machine K whose language is HP, we mean this is just the expansion of this statement. It says that this Turing machine K, when given any pair MX, will halt and accept if M halts on X. M, when you start M on X, it will either halt and accept, it will either halt and reject, or it will loop. If M halts on X, whether accepting or rejecting, your K will accept, because it is testing whether M halts on X, right? If M loops on X, then my Turing machine K will actually halt, and it will reject this pair mx. So it is doing some sort of analysis of this mx pair and finding out whether my Turing machine L is so badly designed that it is going to loop forever on x, and in that case it will reject such mx pair. So it's giving you the termination of m on x. That is what it is determining, right? And we have assumed that there is a terminating Turing machine, there is a total Turing machine which is analyzing this question whether Turing machine M halts on x or not. This is what we have assumed, that such a k exists. Now the next thing we do is, given such a k, k is given as a 9 tuple of this Turing machine k. We don't know what that k is, but it will have some 9 tuple. Making use of that k, we will construct another Turing machine called n, right? So we will do some surgery on k and we will construct another Turing machine called n. Now I don't give you the 9 tuples of n. We will easily be able to construct it, but I'll tell you what is the behavior of n. So this n will actually work in 3 phases. In the first phase, so this n, Turing machine n, will take some x as input on its input tape, right? It will be given some x on its input tape. What will n do? In phase 1, it will first take this x, put up separator symbol hex and make another copy of x. So your work tape, which initially contained x, will now contain x hash x at the end of the first step. You just have to copy this x out. After adding a hash, you copy this x, and that can easily be done. You can design some transitions which will do this. So my phase 1 is going to transform input x into x hash x, right? After this string appears on the input tape, you fire the Turing machine k on the tape. So you make exactly the same moves as k. So what this Turing TTM k that we assumed exists. So now k will actually work and do some finitely many steps. Now k is a total Turing machine. So on this string it will either accept or reject. It cannot loop because it's a total Turing machine. So k will either accept or it will reject. If k accepts, that is k reaches its accepting state t, then in n we will go to a third phase where n will just loop without looking at input. It will just loop. So if k accepts, then in the third phase we will make n loop. On the other hand, if k gives the answer reject, then we will make n accept. That is, we will go to the accept from the rejecting state of k. In one step we will go to the accepting state of n. So actually whenever k rejects, n will accept, and whenever k accepts, n will loop. So n is a funny machine. It will either accept or it will loop, right? This is what is its behavior. So once again, let me tell you the construction of n. What we have done is, given this, and one more thing I want to state, that given this 9 tuple representation of k, or in other words the code of k, we can construct code of n. It is always possible for us to do surgery on k and add the first phase, which will duplicate x into 2 phases, then run k, and at the end, based on whether k goes to its accepting state or rejecting state, add a third phase which does this blue part, right? So we can always, given k, extend it to define this new Turing machine n, right? So what is this n doing? It first duplicates x into 2 copies separated by hash, then it will run k on this input, okay, and if my Turing machine k accepts, then I go to third phase where I loop forever, so I don't terminate. On the other hand, if k rejects, then I will make my n accept. That is, I will turn this reject decision of k into accept decision of n. So my machine n behaves differently from k. This is diagonalization. Just as we had, x does not belong to f of x in the previous example, here we have whenever k rejects, you are accepting, and whenever k accepts, you are rejecting by looping, right? So we can always construct, if somebody gives us k, we can construct this machine n, right? So this is like first 2 steps in this thing. We just want to construct this n. Now we ask some question. Suppose we have this Turing machine n. This Turing machine n will have some code. Every Turing machine has a code. We saw how every Turing machine's 9 tuple could be written down in form of its code. What happens if we load this code of n onto the input tape and then we fire this machine n? Okay. may sound to you why we are doing all this, but just see, no? I mean, after all, we have constructed this machine n, this n machine n. On given this input code of n, it should do something, right? So what will it do? I claim that you will wind up into a contradiction. So what will this n do? And suppose this n that you have constructed, n has two possibilities. It either loops or it halts and accepts, right? So if n halts on this code of n, then what is the definition of n? When does n halt? It halts when k rejects. That is, k will reject this n, two copies of n, because what does n do? What does n do? It takes this input, converts it in, makes two copies of it. You know, two copies of x were made, so it will make two copies of this, and it will fire k on this. And if this k, because you know n halts, this k should have rejected. So you can say this is an if and only if reduction. That is, n halts on n if and only if k rejects this step, right? And if k rejects this, when does k reject this copy? You know, here is a Turing machine and here is the data to it. That is, n loops on this. This is the definition of k. You know, when does the k reject? It rejects if and only if the machine, k rejects mx pair if m loops on n. In our case, you know, our m is n and our x is code of n, right? So n loops on n. So you can see this is very simple. You will have to really, you know, you convince yourself that my equivalences follow straightforwardly from the definitions given here, but we get a contradiction. N halts on code of n if and only if n loops on code of n. This is absurdity. How can it halt as well as loop? It has just do one of the two things. So we get a contradiction. And because we get this contradiction, our only assumption that there is a total Turing machine which recognizes HP is false. Everything else is forced in this construction, right? So this shows that there does not exist any total Turing machine which will solve halting problem. That is, there does not exist a total Turing machine which, given pair mx, will tell you whether m halts on x or whether m loops on x. You know, this cannot be analyzed by any terminating Turing machine. This is what this says. So this is a fairly large theorem, and this, for the first time in history of computing, somebody demonstrated a problem which could not be solved by a total Turing machine. That is, a total Turing machine is an algorithm. It always gives an answer. And no algorithm could answer whether a Turing machine halts on an input or not. And this was the demonstration of the first language which was not recursive. It happens to be a recursively enumerable language, but it is not recursive, right? So this is a very, very, very important problem. So what we have is something like this. Page after, if I add, you know what, the picture looks like this. Remember, we had regular languages, right? And then we had context-free languages, CFL, which were there. And then we had recursive languages, right? And we knew that recursively enumerable languages are larger than recursive languages, but we did not know if there was anything here. Maybe these RE languages are same as recursive languages. And now with this Turing's work, for the first time, we have got a language HP which is RE but not recursive. Here what kind of languages we have got? A raised to n, B raised to n, C raised to n. We have also the language WW and many other. In context free, we have languages like A raised to n, B raised to n, or balanced parenthesis or things like. In regular languages, you have got things like A star, B star, C star, right? So we have this hierarchy of languages, and for the first time, we found something which is RE but not recursive. And this was a deep result. Okay, so there are limits to what recursive, that is, algorithms can do, what computers can do and definitively answer. There are these broader classes of computers which will search for an answer, and if the answer is yes, it will find it, but if the answer is no, maybe it will keep searching forever. So there are this kind of languages. But are there languages here which are not even recursively enumerable? That is, no Turing machine can either search for all the yes answers nor no answers. So this question remains, and we will answer that in a moment. It is in fact a straightforward proof. We had seen these two properties of recursive languages, so you should revise my lectures on Turing machine where these two theorems are proved. It shows that if A is a recursive language, then its complement is also recursive. Why is this the case? If A is recursive, then there is a total Turing machine which will say yes on all the members of A and no on all the members of which are not in A. Well, you just switch the no and yes, that is, you switch the accept and the reject state. In that case, wherever the original Turing machine said yes, my new Turing machine will say no, and so what I will recognize is exactly the complement language, and this Turing machine will also terminate. So now I have a Turing machine which is total, which is recognizing the complement of A. By doing surgery on the Turing machine for A, by switching its accept and reject states, we get this. So this theorem we had seen. Second theorem we had seen was that if A is recursively enumerable and its complement is also recursively enumerable, then A must be recursive. Why is this the case? A is RE, so I have a Turing machine which will halt, which will accept on every element of A. Those things which are not in A, the Turing machine may loop or it may reject, right? So what I do is I start a two-tape Turing machine, where the string X I am trying to determine whether it's in A or not. So I will have two-tape Turing machine. I will make a copy of X on both the machines, and then I will suppose the Turing machine for A is called M, and the Turing machine for not A is called N, because both are RE, they will have their own different Turing machines. And then I start Turing machine M on this first tape and this Turing machine N on this second tape, and I run them simultaneously. So I have a multi-tape Turing machine which will do one transition of M and one transition of N simultaneously. Now, since a string has to belong either to A or not A, one of the two machines will terminate and accept. If M accepts, then the language belongs to A. If N accepts, then the language does not belong to A. And this will definitely happen in finite number of steps. So now, by running these two in parallel, I have constructed a multi-tape Turing machine which will tell me whether a string is in A or it is not in A. It will never loop forever, because one of the two Turing machines will terminate. So we also have the property that if A is RE and not A is RE, then A is recursive. We had done this before, right? So what I will do is, now what we can do is, my claim is that take the language not of HP. What was HP? HP consisted of all strings, all pairs MX, all pairs MX such that the language is HP. M halts on X, right? So what will be its complement? All those strings such that M does not halt on X, or some absurd strings. Right? Strings which don't form valid representation. My claim is that not of HP, is a well-defined language. And what kind of language is it? Is it recursive? Is it RE? Is it recursively enumerable? Now my claim is that complement of HP is definitely not RE. Because if complement of HP was RE, then because HP itself is RE and complement of HP is also RE, then HP will become recursive by this theorem. If not of HP, okay, assume not of HP is RE. Now we have already shown that HP is RE, right? This we had shown. If both HP and complement of HP are RE, this implies by this theorem that HP is recursive. But we just showed, by this Turing's diagonalization, that HP is not a recursive language. So we have a contradiction, right? Because HP is definitely not recursive. So this assumption that complement of HP is RE is wrong, and we have got this language, complement of HP, which is not even recursively enumerable. So if I go back to my diagram, here I have got a language which is not of HP. In fact, any language you take here which is not in recursive, its complement will come outside. So complement of any RE language which is not recursive is non-RE, right? This is what this theorem proves. So if A is RE and A is not recursive, then sorry, then tilde is not RE, right? This straightforwardly follows from these two theorems. Okay, so this is an important property, and it shows that whatever is there in this diagram, in this place, in the RE part which is not in recursive, its complement will come here. Okay, this may have many more things, right? So that is the question. Okay, so I have done, I have shown you that what we have done so far are some very deep results. It shows, we have shown by using diagonalization that the language HP is not recursive. We have done that by constructing, assuming that there is this total Turing machine for HP, and derived a contradiction by constructing this machine N by doing surgery on K. And then we have asked a question about N, which leads to, if K exists, N must exist. And then we can ask this question about N. And this question has, leads to absurdity, to contradiction. Hence, such an N cannot exist, and hence such a K cannot exist. That is what we show. And once we have this language HP, which is RE, its complement, which is not recursive, its complement is not even RE. So these are all non-RE languages, right? We have shown existence of such things. But this halting problem is, so, is halting problem one rare language which is in RE and most interesting languages come here? Well, fair number of useful languages are recursive. But what about languages here? What else is in RE, right? So we will look at one more example. And we had these two problems, HP and MP. We know both of them are recursive. We also know that complement of HP is not RE. What about MP? Is it recursive? We have already shown that HP is not recursive. What about MP being recursive? Well, we can give an argument similar to Turing's argument by diagonalization to show that MP is also not recursive, right? So MP is not recursive. You can give a proof using diagonalization, but such a proof is involved. There is an easier technique and widely applicable technique. Now that we already know that HP is not recursive, we can make use of this fact and prove that MP is not recursive. And to show that, we give what is called proof by reduction of HP into MP. That is, we show that if MP was recursive, then HP would also turn out to be recursive. And we already know that HP is not recursive. So the assumption that MP is recursive must be false. So we'll show how, having an ability to decide MP will give us ability to decide HP, right? And we will show that. So in order to do that, we will do this proof by reduction. So there are these two techniques to prove that there are languages are not recursive. One is by diagonalization, and the other is by reduction to known problems which are not recursive. And since we know, so we will reduce HP to MP. In some sense, we will show that if you have ability to solve MP, you have ability to solve HP. And you already know you have no ability to solve HP. So you can't have ability to solve MP, right? Okay, so what do? We effectively given an MX pair, we want to check whether it belongs to the language HP or not, right? We want to decide whether this MX pair belongs to this HP, language HP. That is, whether machine M on X halts or not, right? This is what we want to decide by a total Turing machine, right? What we do is, we effectively translate such an instance of an HP question into an MP question. That is, we do some surgery to this MX pair. We don't know the answer to this question, but we will do some transformation of this MX pair and generate a new pair called NX. Okay, and this transfer problem we will give to this MP machine, right? Assuming that such an MP machine exists. So we will not give the original problem to MP, but we will transform the problem MX into NX and give it to this MP, right? And we want to build such a translator which for any given MX pair will, produce this transform string in finite number of steps. So when we say effectively translate, we mean there is a total Turing machine which takes this on the input tape and it finishes in finite number of steps without looping, producing this question on the tape. It ends with this string on the tape, right? So we can transform this question to this question using a total Turing machine, right? How do we do this translation in order to reduce HP to MP? We do the following. Given this MX part, we change the X part remains as it is. The M part changes. The machine description, the 9 tuple of the machine M is changed to some different 9 tuple of machine N. All we do is we examine the transition table of M, and every transition of M which goes to R, we will redirect it to go to T. So now no transitions in this transformed M, which we call as N, are going to the reject state. Instead, they are all going to accept state. So when you go to accept state, basically you are determining whether M halts on X instead of whether M belongs to X or not, right? So you got this transform problem which halts. If M halts on X, then my transform machine N will accept X. And if M does not halt on X, my transform machine will loop forever, just like M. Right? So my N is, M had 3 possibilities: accept, reject, or loop. N has only 2 possibilities. Whether M accepts or rejects, N will accept. And otherwise it will loop. And I can easily change the code of machine M to the code of N with this property, right? So this is the transformation we have done. And it's easy to do using a Turing machine. It will just scan through the transition table, and for every rejecting transition, it will redirect it to accepting transition, right? The translation has this property. If MX belongs to HP, then the translation of MX belongs to the membership problem, if and only if. If it does not belong to HP, this will not belong to membership problem. So you can convince yourself that this property holds, right? And then my claim is that if MP is recursive, that is, if we have a total Turing machine deciding MP, then HP will also become recursive. Why? Because in order to decide whether a pair MX belongs to HP, first I will apply this translation Turing machine, which will transform MX to NX, and then I have a total Turing machine answering MP. So I will use that Turing machine to check this. And if my MP says yes, then I know that my then MX should also belong to HP. So I solved the halting problem, with a terminating Turing machine. So by combining this translating machine and machine for MP, I am able to solve HP also. So if MP was a total Turing machine, my constructed machine, which composes the translation machine, M sigma I will call it, followed by this MP machine, will give me machine for HP. Let me call it MMP, machine for MP. Machine for membership problem will give me machine for halting problem. And that cannot exist because, there is no total Turing machine which will solve HP. And my only thing I assumed was there was a total Turing machine for MP. So that must be wrong. So I can now conclude that MP is also not recursive. We already showed that MP was recursively enumerable. So here is another language which is RE but not recursive. So if I go back to my diagram, I can add one more element here. MP is also here. And so not of MP will come here, right? So I've got 2 more things here, right? In fact, this idea that we have done, that given a new problem, that we want to check whether it is recursive or not, we can take a known problem which is not recursive and reduce it to this problem, and thereby show that this problem is also not recursive. This is institutionalized in a method. So this is the proof I gave in a method called many-to-one reductions. Now this part of the course is optional, and I think it's a very interesting part of the course, but we are running out of time. So you can study this many-to-one reductions only for interest. Okay, let me do that. Okay. So we will formalize the kind of reasoning we gave here to prove that MP is not recursive. as you know, since we know that HP is not recursive. We did this by reducing HP to MP, and we did this by translating an instance of HP problem into an instance of MP problem. Okay, that is what we did. Now we can do this systematically for many problems. So suppose you are given a language A, which is a subset of sigma star, and another language B, which is a subset of gamma star, right? We define something called a function sigma from capital sigma star to capital gamma star. That is, it translates an instance of, our problem is to decide whether an element of sigma star belongs to set A or not. And there is a corresponding second problem which says an element of gamma star belongs to B or not. And we are going to look at ability to solve the A problem using the ability to solve B problem by translation. So suppose we have a function sigma which translates every string in sigma star to some string in gamma star. Such a translation sigma is said to be many to one reduction of A to B, problem A to problem B, provided these two conditions hold. So certain kind of maps from sigma star to gamma star are said to provide many to one reduction of A to B, where A and B are given to you, if the following two conditions hold. Firstly, this function sigma is a total function. That is, every string in sigma star is translated to some string in gamma star. And secondly, it's a computable function. That is, there is a total Turing machine, which realizes sigma. That is, if you give the string sigma star, string belonging to sigma star on the input tape of this total Turing machine, it will terminate in finitely many steps and end with the result sigma x on the tape. That is, this translation can be achieved using our total Turing machines, right? And secondly, this translation has the following property. If x belongs to A, then sigma of x must belong to B. That is, every member of A is mapped to some member of B, and every member which is not in A is mapped to something outside B. So, if you have got sigma star which looks like this, and this part is A, and this is your gamma star, and this part is B, then everything in A goes to something in B, and everything outside A goes to something outside B, right? So yes instances of being in A are transformed to yes instances of being in B, and no instances of being in A are transformed to no instances of being in B. This kind of maps are called many to one reductions, right? And they have to be total and computable, and they have to preserve this yesness of membership in A and B. Some notation should remember. If there exists such a function sigma, which is a many to one reduction of A to B, then we will emphasize that by writing like that. That is, sigma is a map, which reduces the set A in a many one fashion to the set B. So this says sigma is a many to one reduction from A to B. This is what we will use to say this, right? This is just a notation we will use to state that, this sigma is a many to one reduction of A to B. Instead of writing that long English, we will just write this. And secondly, we will write such a thing to denote that A is many to one reducible to B. That is, there exists some many to one reduction sigma which maps A to B, right? We don't know, we are just stating the existence of such a map. So these two notations we will be using. Okay. Now, just look at this definition very carefully. Now, something should be obvious to you. Suppose you had ability to determine whether some element belongs to B or not using a total Turing machine. That is, the set B is recursive. Then my claim is A is also recursive. Because what I can do is, I can always compute this translation sigma, which will by a terminating Turing machine. So I'll take a string which is in sigma star and translate it using sigma, and resulting string in gamma star I will give to the total Turing machine which solves B. So I get a total Turing machine which solves A, because the resulting Turing machine will solve the membership in A using membership of sigma x in B, right? Membership of X in A can be solved by solving membership of sigma X in B. And we have a total Turing machine for B. And this translation we can do using our total Turing machine. So we have a total Turing machine which will solve this. So you see, once you have many to one reductions, you get ability to solve A using B. On the other hand, unsolvability of B will also imply unsolvability of B. So here are the formal properties. Suppose it is the case that A is many to one reducible to B, then if B is recursively enumerable, that is, there is a Turing machine which accepts elements of B, and on elements which are not in B it may loop or reject. I claim that A is also recursively enumerable. Why? Because I take the translation of A to B, that is a total Turing machine. So every instance of problem, whether you are in A or not, I first translate to a problem whether I am in B or not, and then I fire the partial Turing machine for B. So I get a partial Turing machine which will solve membership in A, right? So this is just the argument I go. There I had given argument. So there is this other theorem also. If B is recursive, then A is recursive. And if B is recursively enumerable, then A is recursively enumerable. These two properties I get. Okay. I think this should be immediate to you. So I hope you have understood these two properties. Now what is the this is an if-then statement, right? So we can write it in contrapositive state form. You know, if you have got if P, then B, if this is there, then it is also true. Therefore, if not B, then not A. This is a fact. If this is a fact, this is a fact. This is called the contrapositive version of this conditional statement. So if we apply this if-then statement in contrapositive, we get the following result. If my set A is not RE, so negative of this, negation of this conclusion. If A is not RE, then B is not RE. That is, if A is not RE, then B is not RE, right? That I can show. It is same statement as this. And the contrapositive of this, if A is not recursive, then B is also not recursive, right? So this theorem lets you, take some known RE languages and construct some other RE languages from it by many to one reductions, and by taking a language A which is not RE, such as A, it allows us to prove that B is not RE, right? Or if A is not recursive, B is not recursive. So this theorem allows us to prove many other languages as RE or not RE or not recursive by such reductions, right? So we show that HP is many to one reducible to MP. How did we show that? We showed it here. We gave this translation, of HP instance to MP instance. This sigma that we constructed is actually a many to one reduction. You can check that the two conditions are implied. If there is a yes instance of HP, it will transform to a yes instance of MP, and if there is a no instance of HP, it will transform to the no instance of MP. So check this for yourself. So my claim is that this sigma that I gave here was a many to one reduction from HP to MP. We gave that, right? So this fact we have to check, and we had shown it earlier. Since HP is not recursive, by the contrapositive form of this, if HP is not recursive, then MP is also not recursive. So because HP is not recursive, we automatically get that MP is not recursive, and that is what we used in that earlier argument. But here, using this theorem, we get the same fact. Okay. So this is how we do many to one reductions, and the exercise is that you show that membership problem MP is also many to one reducible to HP. Okay, so you can show this, and since we know HP is recursively enumerable, this will show that MP is also recursively enumerable. Okay, so we have this kind of properties that we have derived. In fact, you can apply this to many other problems. And in fact, the typical kind of problems that we want to apply this kind of, whether these languages are RE or recursive, are problems about Turing machines. So here I define a language called MT, and MT is a collection of Turing machines, or rather codes of Turing machines. And these are all those Turing machines whose language is empty. That is, they are complicated Turing machines, but ultimately they don't accept any string. They may either keep looping on any string that you give it, or it may go and reject that string. So no string is a member of the language of that Turing machine. I collect all such Turing machines, right? And I get a language called empty. So empty is a collection of Turing machines. Just as HP was a collection of Turing machine and input pair, I have here a collection of Turing machines. Fin is another collection of Turing machines whose languages are finite. That is, they accept only finitely many strings, right? So here I have 2. And if you look at Cozen, he gives a list of some 10 different collections of Turing machines. And the question is, what kind of languages do this form? So are these languages RE? Are these languages recursive? Or are they non-RE? Right? Are they not recursive but RE, or they are non-RE? Where do they belong in our diagram? These questions are there. And it turns out that you can show that if you take the complement of halting problem, you can do a many-to-one reduction of the complement of halting problem to this language empty. Okay? And you can also give a many-to-one reduction of the complement of halting problem to this language Fin. Now what does that imply? Let me give you 1 minute to answer. We know something about not HP, that is complement of HP. It is a language which is not RE. So by this theorem, this part of this theorem, if A is not RE, then B is also not RE. Now we know HP is not RE, so empty is also not RE. Similarly, not a complement of HP is not RE, so Fin is also not RE. So using this theorem, we have populated our diagram, by empty, not RE, empty and Fin. And in fact, there are a very large number of languages which are, properties of collections of Turing machines or Turing machine, input pair, which will lie either in RE or, not RE. Very few collections of Turing machines belong to this recursive set. So, collections of Turing machines satisfying certain kinds of properties, largely belong here. And there's a theorem which exactly characterizes what are these languages. It's called Rice's theorem, but it is out of scope for us. So I just wanted to tell you this. Now, the fact that Fin and empty are not RE depends on showing this reduction. That is, something is not something belongs to complement of HP can be reduced to something belonging to empty. And this many-to-one reductions are exhibited in this proof here. Now, I think you can study this proof only for interest. The proof is not in syllabus. You can remember these facts, but let me do the proof for those of you who are interested, and others can skip this. So what do? What are members of not HP? They are pairs, MX pairs. And an MX pair belongs to not HP if M does not halt on X. If it halts on X, it belongs to HP, and so it will not belong to complement of HP. So these are all MX pairs where M loops on X, right? Given such a pair, we translate. We don't know whether M halts on X or not. But given any such pair MX, we will, by means of a total Turing machine, we will translate this to a Turing machine N, right? So given MX pair, we will translate it to N. And what does N do? This N that we will have obtained will behave like this. So, given the 9 tuple for M and this X, we will construct the 9 tuple of N. But this Turing machine N that you have constructed will behave like this. Suppose you start N with Y on the input tape, then what it will do is following. It will firstly erase this Y from the tape. So it will ignore what Y you gave it, right? Next, it will go and write X on the input tape. So it will replace Y by X on the input tape. And then what it will do is, it will start mimicking M on this X. That is, the transition table of N will have same transitions as transitions on M. So in the first phase, it will erase Y and write X on the tape. In the second phase, it will just run the transitions of the Turing machine M, right? And then what happens if this M halts, whether accepting or rejecting, our machine N will accept, right? This is how it will behave. If M does not halt, it goes on forever. N will also have to loop forever, because it is emulating M, right? So clearly, if M loops, then N loops. So this is our behavior of machine N that we can easily construct, as a 9 tuple given the 9 tuple of M, right? So I think you should study this construction. And then the question is, what is the language of this Turing machine N that we have constructed, right? There are two cases. We have constructed this N given this MX pair. So for different MX pair, we will get different N's. So MX is a parameter of N. We'll get different N's for different MX pairs. Looking at MX, we have constructed N, right? Because we are going to run that M. If M halts on X, in that case, what will happen? If M halts on X, whatever Y you gave initially onto the tape on N, it is going to erase it and run M on X and halt, and so the N will accept, right? So any Y that you give will be accepted by N. So the language of N will be sigma star. Any arbitrary string Y will be accepted if M halts on X. On the other hand, if M does not halt on X, then this N will loop, because M will loop. M does not halt, so M will loop, so N will also loop. So I have constructed an N which has this property. Based on Mx, I construct N such that if M halts on X, then language of M is sigma star, which is infinite, certainly not empty. And if M does not halt on it, I get an empty language which is also finite. So now you can check that this transformation from HP is a many to one reduction to empty. The same reduction is also a many to one reduction from complement of HP to fin. So this translation that I have given actually gives you simultaneously a many to one reduction from not HP to empty and complement of HP to fin. And hence, because we know not of HP is not RE, this is also not RE and this is also not RE. So we have proved that these two languages are so complicated, no Turing machine can, even semi-decide them. Okay. So that is the last thing I wanted to do. So we covered quite a bit of material. These are amongst the advanced results on theory of computation, and I urge you to appreciate the intellectual depths of this result. So what we have done in this course is that we have studied a hierarchy of languages and hierarchy of machines. So first we studied very simple class of languages called regular languages. Now what are the machines for this? For regular languages, we had FSM, which are also equal to epsilon NFA, right? So we had DFAs and NFAs which recognize this. For context-free languages, we had push-down automata, right? For recursive languages, we had total Turing machines. And for RE languages, we had Turing machines which are potentially partial, right? And for these languages, unfortunately, no mechanical computer can check membership into these languages. So there are many languages here. So there are lots of problems which are not solvable by computers. We only know, they exist in mathematics. Okay. So that is what I would like you to appreciate from this course. Okay. Thank you. I will stop this recording and hopefully